which works like this. We will have 3 short talks, 10 minutes in length. They will follow each other without a question session, and we will have the question session after these 3 talks. So if you have questions, write them to the chat, the YouTube chat. They will be collected, and then in the end, the discussion will be with all the 3 flash talkers. And with that, I am happy to introduce Manel Ripoll, also from I call it AC2T Research GmbH, so working at the same company as Georg, who will talk about friction control in extreme environments using laser deposited self-lubricating alloys. And with that, Manel, you can share your screen and you have the stage.
Okay, let me see if it works.
That looks good.
Okay. So thank you very much for the introduction. In this flash talk, I would like to share some snapshots of the work that we have been doing in the past years on the development of self-lubricating alloys made by laser deposition. And this work was mostly done by our colleague Hector Torres, who was at that time a PhD student, and now he is scientific staff with us. So why do we need self-lubrication in extreme environments in particular? Well, the point is that there are some applications like aerospace or high temperature forming processes where lubrication is challenging. It's not impossible, but it's very demanding. In aerospace, for example, we have vacuum, so we have outgassing of conventional lubricants. So due to the vacuum, it's complicated to have some efficient lubrication. And also at high temperatures, conventional greases and lubricants degrade very quickly at temperatures over 300 degrees. And there are other alternatives that are always coupled with disposal, safety issues, and also environmental issues. So in those 2 applications, the use of materials that are able to have some intrinsic low friction would be of a very high advantage. And why laser deposition? Well, laser deposition is one of the additive manufacturing techniques. It's called laser metal deposition. And basically by these techniques, we can produce layer by layer several samples. It doesn't have the precision of other techniques, like for example, selective laser melting, but it can produce very large and bulk materials, and it can also be used for repairing and refurbishing. So it's also a very efficient technique in this sense, because it's also cost effective. It provides, for example, when you use surface functionalization, it provides functionality only in that places where you need it, which also can be very convenient in many applications. And it also can be coupled together. It fits very well also with other additive manufacturing techniques. So like, for example, in this example here in the bottom, so let me put the pointer. So in this sample here, you can have a sample manufactured using, for example, selective laser melting, and on top of it, you can have a laser metal deposition for surface functionalization. So this is a very convenient method, very modern approach. It's a novel manufacturing approach, but it also has some challenges in the material deposition. The point is that, for example, if we have a nickel-based alloy and we want to make it self-lubricating, we need to add some solid lubricants. For example, silver is a soft metal with a good shear, with a low shear properties, but nickel and silver, they are not miscible. So if we melt them with a laser, we end up having some microstructure like this. So it's a substrate with a nickel-based coating with a huge silver bubble on top of it. So this is completely useless. So it's just a fancy way of wasting silver. So if we want to have something useful, we need to have this solid lubricant homogeneously scattered and distributed in the microstructure. And to do this, we need to have some diffusion barriers for the silver, and we can do it using, for example, sulfide compounds. So in our case, we use molybdenum disulfide that during the thermal deposition decomposes into chromium sulfide. This means that it's not limited, this process, to molybdenum disulfide. It also can be used other sulfides as a precursor. But once we use these sulfur compounds, we end up having this microstructure with the characteristic nickel, dendrites, the silver, like these light gray silver inclusions that are surrounded by these dark gray chromium sulfides. We can see here the transmission electron microscopy image with more detail. You can see here this chromium sulfide compounds, the silver inclusions. This is pure silver. This is also important that silver remains as a single phase, doesn't build any intermetallics. And in the nickel matrix, we see just very little sulfur going in the form of leftover molybdenum disulfide and also of the degradation product molybdenum tetrasulfide, which is non-lubricious. So we check this nickel self-lubricating alloy under different conditions. So the first one is, for example, reciprocating sliding model experiments against martensitic stainless steel. We always use some material as a reference. In this case, we use also martensitic stainless steel. Cladding as a reference, this is the red line. And we can see here that when we use the martensitic stainless steel, friction is very high. And when we use, for example, the nickel-based alloy, we have the green lines, we are able to have a very steady and low friction. For example, look here at 400 degrees, we can have a metal-to-metal contact at 400 degrees without any lubricant and a steady coefficient of friction of 0.2 compared to close to 0.6 for the martensitic stainless steel. So very good friction performance, and at 600 degrees still managed to get some good performance, much better than the reference alloy, but already struggles a bit. We also try close to reality tribometer that it's available at Luleå University of Technology in Sweden. In this case, we have a strip test with aluminum silicon coated ultra high strength steel at 700 degrees, and we do always single pass, replace the sheet and use a new one. You can see here the results, and you can see that when we use a reference, in this case was a nickel based material without any solid lubricant, friction is high, and also we have these break-ins into the coating in this aluminum silicon coating, which spikes of friction close to 1. And when we use the self-lubricating one, in this case the blue line, we have a much lower friction, around 0.3 for every sheet, and when we change the sheet, we also don't have this break-in friction. We also get a change into the lubrication mechanism, into the wear mechanism, sorry, and we switch from adhesive wear, which is very detrimental in forming processes, to mild abrasion. Another example, also in this case, model experiments, reciprocating sliding against aluminum alloy. In this case, aluminum, forming of aluminum is very demanding, so we added some solid lubricant and check what happens when we have a lubricant starvation. And you can see, for example, a tool steel starts here with very low friction, but as soon as the solid lubricant fails, friction skyrockets and goes over 2, and we need to stop the experiment due to extremely high friction. And with the nickel base, the blue line, we see that initially friction is low due to the solid lubricant, then you end up building a tribofilm, and at some point friction gets very stable with a value of 0.5 and could continue during a much longer period. And also in this case, we see that we switch from adhesive wear to mild abrasion. But where these nickel-based materials really shine is in vacuum. So in vacuum, we test it against 440C, the martensitic stainless steel. This is the reference material for vacuum experiments. And this is a pin on disc, but don't be confused because it's not unidirectional. It's reciprocating sliding, so we are moving around an arc of circumference with a constant normal load and at 2 different temperatures, room temperature and 300 degrees, without any solid lubricant, without lubricant at all. So completely dry contact. And what we can observe here, so the reference nickel alloy in room temperature or at 300 degrees has a really high coefficient of friction, very unsteady with these spikes that are characteristic of metal-to-metal adhesion. And when we have the nickel-based self-lubricating material, we see that friction is very low, around 0.25 at room temperature and slightly below 0.2 at 300 degrees. So again, this is metal-to-metal contact in vacuum at 300 degrees without any lubricant at all. And in this case, what we can observe also is that not only the friction is much better, but also the wear is much better. In this case, we have, for the reference, nickel-based cladding, severe plastic deformation, we have an irregular wear track, and we have the self-lubricating nickel cladding. Friction is very, very small, very homogeneous wear scar, and very, very narrow, very thin, And we can see here in the scanning electron microscopy image how this smearing of silver that is supported here by thermal softening at 300 degrees helps and aids in controlling friction at these temperatures. And now I would like to leave the last two slides with a bit of outlook. So what are we doing right now? And we thought, okay, have a nickel self-lubricating material is cool, but actually it would be much cooler to have the self-lubricating titanium alloy. So titanium is a superb material, excellent strength to weight ratio, very good corrosion resistant, but have really miserable tribological properties. And the idea is, would it be possible to have a titanium alloy with some self-lubricating properties? And we end up with this microstructure here. So this is a titanium 6 alloy, titanium 6-4, titanium grade 5 alloy. And basically these light inclusions here, this is the solid lubrication phase, which is the titanium nickel rich phase. And when we use this under reciprocating sliding at high temperature in a self-mating titanium contact, so very detrimental contact conditions, we see that friction, particularly in the range to 400 to 800 degrees, is far better when compared to the self-mating titanium contact. Even at 800 degrees, we need to stop the experiment here. In this one with a very high friction, but still continues running. And the best conditions for this self-lubricating titanium alloy is at 600 degrees, where we get a coefficient of friction relatively good and low at around 0.5. Again, self-mating titanium alloy without any lubricant at all. And finally, we came to our colleagues from Tallinn. They are working in this powder metallurgy, developing titanium borate composite materials, and we apply also this nickel bismuth addition, and we ended up having this titanium borate titanium phase surrounded by bismuth, and this bismuth phase is surrounded by nickel. And we repeated these experiments, also very detrimental conditions, self-mating titanium contact, and we see that in this case, especially at the lower temperatures, room temperature and 400 degrees, friction in a titanium self-made contact can be as low and steady as 0.4. And not only friction gets better, but also compared to the self-mating titanium contact, the wear becomes also much better. So with this, I would like to conclude. So I have shown you our initial self-lubricating nickel alloy that works by encapsulating metal sulfides on silver pockets, that it provides very good friction control in air until 600 degrees and 300 degrees in vacuum, friction reduction in different forming processes, and now our current work on self-lubricating titanium alloys. So with this, I would like to thank the Austrian COMET program for financial support, and also thank you very much for your attention.
Thank you very much for that interesting topic, Manel. And then, yes, we will move directly on to the next presenter, who is Andrea Silva from SISSA International School for Advanced Studies in Trieste, Italy. We'll talk about design principles for crystalline interfaces, directional locking, directional superlubricity, and structural lubricity. And with that, the screen is yours.
Thank you for the kind introduction, and allow me to present our work. You can all hear me, I assume, and see the right screen.
That is correct.
Perfect. Okay, so yes, I'm Andrea Silva, working in SISSA, and I will now bring you a bit down to a smaller scale, dealing with nanoscale friction, and a bit more theoretical as well, as we are computational people in Trieste. So the realm we are dealing with is that of nanomechanical devices, so a strive of engineering to miniaturize our technology, let's say. And in this world, there are normal processes that become very intriguing, like nanoscale peeling and bending work very differently than what we are used to in the macro scale world. And especially nanoscale sliding is completely different than what we are used to. And in particular, it presents itself usually in the form of stick slip or structural lubricity, so contact with high friction and violent events, or contacts where the two things can slide freely against each other. And these are characteristics that are important to know, because like if we are building a machine on the nanoscale, we want to be sure that it actually stays in the place we put it, or it can move freely as we want it to. And these two behavior are linked by something is called the Aubry transition that can also mix one with the other. And all this nanoscale sliding is sort of controlled by the moire pattern that develops at this crystal-crystal interface. And the zoology and the variety of these patterns and specific crystal interface is very big, as we saw in the talks on Monday. So it can be probed by high throughput density functional studies, and where you can compute the potential energy surface of two crystalline interfaces sliding. And it has also been probed in the experiments where, for example, here in the case of gold island sliding, molybdenum disulfide island sliding on gold, the system is pushed always in the same direction, but it goes along preferential direction due to the crystal symmetry. So there is some directional locking of the motion. And at this small scale, it's also very important the effect of finite size, as it was shown in 2013 by Ditzel. When you study the friction as a function of size, you see that the friction scales according to specific rules, and in particular, structural lubricity, where the friction disappears in an infinite contact, is shown to display this sublinear scaling with the number of atoms. So the realm of the sliding friction and nanoscale, it's complex, and even to explore it, we need some guidance. And that's what we tried to do recently, trying to define a degree of commensuration and trying to answer the question of, given an arbitrary interface, by which I mean two mutually rotated lattices, what is the qualitative friction behavior to expect? So not going quantitative, like it's a step before high throughput, let's say, but like in general understanding what would be the friction to be expected by this contact. So we work on a geometrical level to be general and fast. And now I will try to summarize a lot of math, let's say, in a visual way. But first, let's build a system. So we have our system is built from a substrate potential, which has a general form and is periodic with whatever periodicity we want it to be. And there is a reciprocal space associated to it. So the Fourier transform of the real space. So we put above the substrate our adsorbate, building our crystalline interface. And this would be a second lattice with a different periodicity that can be rotated at an angle and is associated with an adsorbate reciprocal lattice as well. So the red point here. The frictional quality of the contact at this nanoscale contact, at least in this theoretical extended word for now, is given by the appearance of a coincidence lattice vector, which is when the two lattices match, and so that they can interlock nicely and give rise to high friction or structural lubricity. So these coincident lattice vectors are related to the moire I was saying before, that gives the quality of the thing, and we can reduce these lattices to understand the moire symmetry of the contact. And by translating the adsorbate lattice over the substrate, we can compute the translational energy landscape of such a crystal interface. So in this case, we will have directional locking, so the system will move along the preferential direction of the substrate. And just to get a bit more detail, this can be computed numerically, which is usually done in codes by really summing over the atoms building up the interface, or we did it by using a Fourier transform of the potential, which is an exact match in this periodic infinite system. So this is the case of directional locking, where friction is high and you expect stick slip. On the other hand, we would have structural lubricity, where the system can slide freely in any direction. So the energy landscape that we see here is flat. This means that the two lattices are incommensurate, but there could still be, mathematically, there could still be coincidence lattice vector in real space, but if there are none in the reciprocal one, then you would expect to see this sort of flat energy landscape. And in this categorization, we discover an intermediate novel type of interface, which we call the directional superlubricity, because for specific lattice symmetries, you would have only one coincidence lattice vector, and the moire pattern would be form of dense line spaced over discrete spacing, which results in this energy landscape, which is made of valleys and ridges, where the friction is exactly zero along this valley, but retains a finite value on the, perpendicular to it. And just to go a bit back to the real world, let's say, the first case would be the one of graphene sliding on graphene, where you translate the upper layer, you go through different configuration and you have like minima and maxima alternating. Or to give an example with the same symmetry would be nickel on nickel. The case of structural lubricity would be, for example, molybdenum disulfide sliding on graphene or HPN, because they have a large incommensuration. And we are not aware of anyone reporting a theoretical study on this directional superlubricity with this specific friction anisotropy and the scaling law I'm about to show you. As I said, like scaling law is kind of what defines structural lubricity, going from finite size, increasing the size and the sublinear scaling. And we can describe that with this approach. So if we take a finite flake of size n, we can write the potential energy surface in real space by summing over the particles, or using the reciprocal lattice depicted down here. So we can expand in the Fourier components. And this is for a finite size flake that will go back to the one I showed you before for an infinite system. So here there are a bit of formula, but they can be broken down a bit. So the important bit is like here we have an arbitrary form of potential, just needs to be periodic, and we can write equivalently the system with in the Fourier space. The spatial distribution is given by these plane wave terms here. And at finite size, we have this weight. So all the Fourier components, which means any possible modulation of the corrugation, enter the system, but they are weighted by the specific shape and size of the flake. And in the infinite limit, this needs to give back the categorization I explained before, because this weight will just select the relevant Fourier component, which here are these matching vectors defining the moire pattern of the system. At finite size, all other components can contribute as well. So we have superposition of different modulation. So for example, we can check what happens to these other two substrate lattice vectors, so these other modulations. And we can describe analytically how these decay towards the infinite limit. So like we have like a constant term here, which is the coincidence lattice vector, and a decay term, which won't be seen at infinite size, but still very much affects the behavior at finite size. This is all a bit like confusing, I imagine, but I think it's very well visualized. So if we take a small flake and we drag it around the substrate, like here, we see that like the energy landscape is very complex, and there are many different periodicity and modulations on it. As the size increases and the system realizes its true incommensuration and the other Fourier component decay, we move towards the infinite limit of the interface. We can play the same game with the new directional superlubricity we discovered. And by increasing the size, we go from a clearly directional lock with like jumping between the minima of the potential, which are the black spots. This starts to develop friction anisotropy, and in the end, we have this true and valley energy landscape. Now we can go back to a bit more friction and measure the friction along the two directions. So if we go parallel to the valley or perpendicular to them. And what we find is that the friction scales very differently. So we have a finite friction per particle, so it's constant, perpendicular to the valleys, while along the corridor, as the size increase, these scales sublinearly. And we tested numerically how this goes for different shapes, and we see that it nicely stays between the theoretical boundary, which has these two lines. So we're still very much in a theoretical world. I just wanted to give a couple of examples where we saw this in a more real system. Not quite a nanoscale interface, but what we call a nanofriction emulator, which is a colloidal system that emulates a real atomic interface, where we have these colloidal clusters over a pattern surface, where we can tune the symmetry and strength of the substrate potential, mimicking two crystals basically meeting and pressed against each other. We can drive it like in a friction experiment using the gravity, and we can see that this cluster move along the pattern surface along specific direction, here going with some directional locking. And if we probe the system along two directions, where we create a system that should exhibit directional superlubricity, as predicted by the theoretical model, we see that the friction along the valley and perpendicular to it nicely falls in between the prediction of the theory. So we are constant when we go across the ridges, and it scales sublinearly with size as we go along the valley. So one last thing that we can do is reverse engineer this process and design an interface with an extreme friction anisotropy. So we can, in this case, we took a graphene substrate and we uniaxially strain along X of about 1.8%, which is well within experimental values. And then we place a HBN flake on top of it. And we can go and see what happens as the size of the flake increases. So the system goes from the usual hexagonal Moore pattern, and as the size grows, it develops this valley up to the infinite limit system where you have perfect valleys in between them. And then we can probe the friction sliding perpendicular to this valley or parallel to them. And we find a scaling of the friction in the two directions, which is very much in agreement with what the theory expects. So there is some, of course, the situation here is more complicated because we use realistic potentials, not some approximated Gaussian. So the system is constant, as constant friction perpendicular to the valley and goes down sublinearly in the other direction. So realizing in the infinite system a very strong anisotropy and structural lubricity only along one specific direction. Using numerical simulation, we can also probe the effect of elasticity, which of course affects the whole system, but this behavior is still retained. There is too much in between. And finally, you can predict also when elasticity will win over this, which for this case, it should be about 0.5 millimeter in linear size according to the critical length estimated by Sharp in 2016. And with this, I just want to thank all the collaborators, and any question we'll take after. Thank you.
Yes, superb. Thank you very much for that very nice presentation, Andrea. And then we will move on directly to the third and last flash talk of the day. Ming Lee of the University of Illinois will present surface structure modulation of agarose-poly acrylamide-co-acrylic acid double. And with that, the screen is already visible. The floor is yours.
Hello, testing.
Yep.
Everything good?
Hear you. Yep.
Okay. Hello, everyone. My name is Ming, and today I'll be talking about how we can control the surface adhesion and friction of double network hydrogels. In particular, my system will be the agarose and polyacrylamide-co-acrylic acid hydrogel system. So firstly, I'd like to try and convince you why hydrogel lubrication is important to us, and then I'll move on to talk about what double network hydrogels actually are, and as well as highlight one advantage of these double network hydrogels. Then I'll move on to what I believe are the core topics for this presentation on tribology, the adhesion and friction control of hydrogels. Osteoarthritis is a common disease around the world where the lubricating layer between our knee joints have been depleted, and the abrasion of these bones result in pain and inability for the patients to walk. If this continues for the long term, it will eject little bone particles called bone spurs, and if these bone spurs circulate around in the knee joint, it will just result in further and more serious osteoarthritis cases. So this is a vicious cycle that keeps getting worse and worse. In addition, the CDC has also projected that this particular disease, arthritis, will only continue to increase as time passes. So this is both a current as well as a growing problem moving ahead into the future. To address this, hydrogels have been proposed as synthetic replacements for cartilage in our knee joint. And I believe there are two important qualities in order for a successful replacement. The first is that the hydrogel must be mechanically strong enough to withstand the compressive stress from our body weight, as well as having a low friction so that you can lubricate the knee bones during joint movement. And that's where double network hydrogels come in. Double network hydrogels are comprised of two polymer networks that are formed sequentially, so one before the other, and they commonly have different cross-linking mechanisms between the first and second network. My particular system comprises agarose as the first network, and then a copolymer between acrylamide and acrylic acid as the second network. As you can see, agarose has a physical interaction. It gelates through hydrogen bonding, whereas for the copolymer, it gelates through covalent bonds. So by controlling these two different interactions, I can time their sequential synthesis to make a double network hydrogel. And double network hydrogels can address one of the problems I mentioned earlier, where hydrogels need to be strong enough to sustain our body weight. Here I'm showing three different diagrams from three different papers. They are explaining the mechanisms of energy dissipation in the double network hydrogel microstructure. But what I want to highlight is that all these mechanisms have one thing in common, and that is the entanglement between first and second networks. So if we imagine like a fishing net, and the horizontal strings are the first network, whereas the vertical strings are the second network, this kind of entanglement between the two networks naturally leads to an enhancement in mechanical properties. Different models have been proposed, but they all have this one thing in common. And that's why I think this is the reason why double network hydrogels are suitable for synthetic replacements, at least in the mechanical space. Next, I would like to start talking about surface characterization, the adhesion and friction properties. And to begin, I'd like to just show you this diagram of AFM, or atomic force microscopy. The way this works is that there is a small and sharp cantilever with a very sharp tip that touches the hydrogel, and then a laser from above would shine onto this cantilever and reflect into a sensor, a photodetector. So as this cantilever travels along the hydrogel surface, the laser spot keeps moving, and that gives us our signal. In the following slides, I'll be showing you quantitative imaging, or QI images. This is a special mode from JPK that allows me to extract three data channels simultaneously: the height, stiffness, and adhesion of my hydrogel surfaces. I'd like to direct your attention to the first diagram on the top, the upper left. And we see a very unique microstructure for my double network hydrogel. It looks sort of like a grain structure, or even like bubble wrap that we have in our shipping containers. The elevated orange grains, I believe, are the copolymer component. So that's the acrylamide-co-acrylic acid component, whereas the black areas that are lower in height, the valleys, I believe are the agarose network. And one reason why I believe this structure appears is that if you look in the second image in the stiffness channel, the valley regions correspond to a higher level of stiffness. And through common knowledge in hydrogel space, we know that agarose is the more brittle and more stiff network compared to the copolymer. So this is why I believe there are heterogeneities in the surface structure. The elevated sides are the copolymer, whereas the lower height is the agarose network. And now I'd like to show you, moving from left to right, I have this one same hydrogel being equilibrated in different concentrations of potassium chloride salt solution. And what I'm seeing, a trend that appears, is that when the salt solution gets more and more concentrated, the height is actually decreasing. The gel is collapsing. And I think that this is due to the osmotic pressure differences. When the concentration is changing, water diffuses out of the hydrogel, leading to a volume collapse, volume going smaller. Next, let's look at the stiffness and adhesion channels. And the stiffness and adhesion are also generally decreasing with the increase in salt concentration. And I believe that this is due to charge screening. And I'll talk more about charge screening in the next slide. Importantly, what I want to show you with this series of AFM images is that adhesion of hydrogels can actually be controlled if we tune the salt concentration that we immerse them in. Now I'd like to talk about the charge screening effects. And the first figure I'm showing is the swelling ratio against potassium chloride salt concentration. Swelling ratio is taking the weight of a wet hydrogel divided by its dry weight when all the water has been removed. So this is a measure that tells us how much the hydrogel is swollen, like in terms of volume. And we see that for the hydrogels, I have 3 different recipes, the 6,4, 7,3, and 8,2. These are just the molar ratios of the copolymer. But in general, as the salt concentration increases, swelling ratio of all these hydrogels are decreasing, but it's getting smaller. At the same time, the zeta potential, a measure of the surface charge of my hydrogels, are also getting stronger and stronger. It's more negative as the salt concentration increases. So what are we seeing here? What's happening? I believe that the carboxylic acid groups in the acrylic acid component, they are being partially screened by the mobile potassium ions in the salt solution, which decreases the apparent overall intrinsic charge of the hydrogel. So with this difference in the osmotic pressure, water would diffuse out of the hydrogel, leading to a smaller volume, and so the swelling of my hydrogels decrease. But wait, I just said that the charges are being screened by the mobile ions. So why is the zeta potential getting stronger and stronger, more negative? This doesn't make sense. And I think that what's happening here is that there are actually competing effects between these phenomenon. As the volume of the hydrogel is decreasing, what we're seeing is that the charge per unit volume, and therefore the charge per unit surface area of these hydrogels are increasing. So the charge density is increasing, and that outweighs the partial screening of the acrylic acid, leading to the stronger zeta potentials that we see here. This has implications on the interactions between the AFM tip, which is the method I'm using to measure these hydrogels, as well as the hydrogel surface. And this would especially affect the adhesion and friction data that we see in the previous and also the following slides to come. Now I'd like to move on to the friction experiments using different concentration of salt solution. And what I'm showing here is on the first row, it is the height channel of the quantitative images that I showed earlier. And then from the second and third row onwards, these are friction maps. So direct visualization of the friction force on the surface of the hydrogels. First experiment I'll be showing is the applied load experiment, where I have fixed the sliding velocity of the AFM tip to 10 microns per second. And then I apply different forces, different applied loads onto the hydrogel, starting as small as 2 nanonewtons that you see in the middle row, followed by 5 nanonewtons, and then there are some intermediate values, and finally ending in 40 nanonewtons and 50 nanonewtons. For your convenience, I have summarized the friction force values into histograms here. So we have water condition on the first column, corresponding to the first row histogram, and then the salt solution condition, which is the second column of AFM images, corresponding to the second row of histograms. And what I'm seeing here is that the friction force is increasing with the applied load. This is as expected. It happens in both soft materials and hard materials. But what's interesting here is that the friction force on the hydrogels have decreased by at least 200 piconewtons just by changing to the salt solution condition. And this ties back to the the charge screening effects that I mentioned in the previous slide, because the surface of these hydrogels have acrylic acid groups, so carboxylic acid, that's COO minus, negative terminated. But then the AFM tip is made of silicon, and it's terminated with the siloxyl groups, the SiO minus groups. So having both negative charges in the AFM tip as well as hydrogel surface leads to repulsion between these measurement devices, and that lowers the friction force that's being measured by the AFM. Next experiment I'd like to show, I have reversed the parameters this time into the sliding velocity experiment. So now I fix the applied load to 10 nanonewtons, but I change the sliding velocity of the AFM tip, starting as slow as 5 microns per second, increasing to 10 microns per second. There are some of intermediate speeds, and then finally ending off with 200 microns and 500 microns per second. Once again, the same positioning of the histogram values I've summarized here. And what I'm seeing is that friction force generally increases with the velocity. And I believe this is due to just viscous dissipation to the solvent. The faster you slide, the more energy you lose to the solvent. And it's a feature of hydrodynamic lubrication. What's more interesting is that I'm seeing 2 friction regimes that are coming out from my friction maps. And in this arrow here, I like to highlight that you can see there are 2 peaks in the histograms, so 2 friction regimes. And I like to tie this back to the heterogeneous surface structure I showed you in the initial QI images. I had elevated grains that I believe are the copolymer, and then valleys that I believe are the agarose. So I think that the copolymer is giving me one range of friction values, and then the agarose is giving me a different range of friction values. This could have potential applications in microfluidics, where you might want channels with higher adhesion and higher friction versus lower friction. To summarize this slide, I'd like to have convinced you that we can decrease friction on these hydrogels by increasing the salt concentration that we immerse them in. And as a side effect, we are also enhancing the heterogeneities of these double network hydrogels. To conclude my presentation, I want to bring across and remind you of two key components of this presentation. The first is that this particular system, agarose-poly acrylamide-co-acrylic acid, has a heterogeneous surface structure with two distinct phases of properties. And secondly, the adhesion and friction of hydrogels can be adjusted. We can control them by changing the concentration of the salt solution that we immerse them in over time. With that, I've come to the end of my presentation. I'd like to acknowledge my advisor, Professor Espinosa, as well as the fellow members of the Espinosa Lab for their help, and NSF for the funding source. Thank you.
So thank you, Ming, for the very nice and interesting presentation. Are there any questions from either anyone in the Zoom meeting or from the chat?
So no one in the chat so far, but Andrea, please go ahead.
I had a question for Manel, actually, for the first speaker. I was wondering if you have any chemical or characterization of really the interface to know what is if there are any phase transformation and what's the chemistry really that forms on the sliding interface of these complex alloys.
Yes, so we have done quite extensive characterization. It's not that trivial, that's the problem. So the talk was limited to 10 minutes, so I could not go into much depth. But besides, so we have here two main components as a solid lubricant for the nickel ones. One is the silver as a soft phase, as a so easy to shear phase, but also the chromium sulfides that are built here, they are also lubricious. Why they are lubricious and when they are lubricious is not really known in the literature. We are working on that right now. But in our last publication, we already noticed that it seems to depend on the stoichiometry of these chromium sulfides. So this, in particular, it seems that the chromium 3s2 and chromium 3s4 might be lubricious, whereas CRS might not be lubricious. These are at least our initial hints. So mostly the tribofilm is consisting on this mixture of sulfide compounds and soft metal.
I see.
But the precise lubrication mechanism is still under investigation.
Because I would not expect silver to mix with sulfur much, but
no, silver remains as a single phase, and that's why it performs at best under vacuum conditions. Because under vacuum condition, it does not oxidize. It does not oxidizes. It remains as a pure metal that's clear, but it does not oxidizes during the process, and that's why it can continue smearing. In air experiments at high temperatures, friction is mostly determined by the chromium sulfides.
I see. Thank you.
Okay. I also have a question which I would just pose to Ming Yun. So your talk was very interesting with the hydrogel friction, and if I understood it correctly, so you mostly go about measuring the friction with your AFM tip. So my first question would be, do you expect the scale effect? So if I would transfer it to the system knee joint, I have like a bigger surface sliding on a bigger gel pad. Would you expect some, let's say, scale effects? And the second thing would be like, are there any like theoretical models or calculation models, maybe similar to what Andrea is doing, of course, quite different materials, but for prediction of the friction in such soft, deformable, osmotic matter?
Okay, so to answer the first question regarding scale effects, one particular problem that we have when we try to measure hydrogel friction with a tip is that if you use too small of a scale, so maybe a very, very sharp tip that we can purchase, what you get is that you will actually puncture into the mesh of the polymer network. And then you get a lot of stick-slip effects, and then the friction maps turn out to have a lot of overblown pixel values. You just see white spots everywhere. So that's the small extreme. And then on the other extreme, on the larger surface area, like you mentioned, in our knee joints, our bones are definitely not in the micro scale. It's different from AFM. So when it comes to the actual applications, I believe that these hydrogels have to be transferred to a more traditional tribology measurement method, maybe those pin-on-disc methods. There have been such reports in the literature where people have tried to use hydrogel as the substrate, as well as hydrogel on the pin itself. They call that the Gemini contact, I believe, so gel on gel. And then they report single values of friction that are averaged over the entire surface of the gel. Unfortunately, I could not do and present that method because of the specific heterogeneities of my system, where I have two phases with two different friction regimes. If I were to transfer this to the traditional method where we average over the entire hydrogel, we would no longer be able to see the specific friction maps that I have shown in my presentation. So perhaps for osteoarthritis applications, we do need to evaluate the gels differently, but I believe I've also highlighted another potential avenue of these hydrogels in microfluidics, where we want specific channels where there are higher and lower friction. And regarding the second, you mentioned calculation of the friction properties.
Yeah, is there like, I mean, the calculation or like a model of somehow to, because it's
in I believe 2018 and 2020, one of my seniors in the lab, Tuba Shoaib, who has already graduated, she studied specifically the physics of friction on polyacrylamide hydrogels. And what she showed was that there is actually a U-shaped relationship of friction against the sliding velocity. So at slow sliding velocities, the adhesive components, the adhesive interactions between your gel and your measurement device, in this our case, the AFM tip, they are predominant contribution to the friction force. So as you increase the sliding velocity, the friction force actually decreases. And then you hit this minimum point. It's like a transition velocity she called V star. And that's where it switches from adhesive dominance to the film, the hydrodynamic lubricated dominance. And that's where I believe most of my data lies. As you increase the sliding speed, friction force increases again due to the viscous dissipation to the solvent. So we see this U-shaped relationship. It might apply to my hydrogel as well, because one of my components is polyacrylamide, but we have not determined that. And also the focus of this particular project is to achieve a direct visualization of friction on the hydrogels, which I believe, to my knowledge, is a first in the hydrogel friction space.
Okay, thanks. Any other questions from the group here?
So I would have one for Andrea. And maybe I just didn't catch that part, but you talked quite in the beginning about the commensurability, and you mentioned that there might be a commensurable lattice in real space, but not commensurable in reciprocal space, and that is enough to get a superlubric sliding. And I always thought, like, okay, if you have commensurability in real space, that's it. Then you're screwed already. But can you comment on this a little bit more? Yeah.
That's what we thought as well. Yeah, that's what we thought as well. Actually, we were pretty surprised where Emanuele, one of the authors, came up with this example where you can have commensuration there, but not in reciprocal space. That is because at the end of the day, like even if you have like that single commensuration point, like the translation in reciprocal space are such that as they move, you will never find it again. It's like just having the origin, but if you translate, you will never end up in the same position, because for any direction, the two lattices drift in a different way, because the vector transform they have a different angle in the reciprocal space. it's a very pathological example where you have like a specific angle between the lattices in real space, but the symmetry is such they transform differently in reciprocal. So you cannot devise a translation that will bring you back to the same point. So in the end, that's what gives you structural lubricity. It's the fact that the translation is not possible, not much what you see in real space.
Okay, thank you. So basically,
I have one question.
expect this to turn up in a real system. But if it would, then it would basically, at worst, give you like some static friction in the beginning if you're locked in this minimum, and then you would just continue sliding, if I understood correctly.
Yes, not even sure if you will be locked in that minimum. It is a very pathological case that you find in this, but it might happen for some very exotic materials in real world.
Okay, I see Manel has his hand up, please.
Yeah, I have one question for Ming. Just curious about the selection of this electrolyte that you use for your experiments, for your measurements. Why did you use this one and not, for example, PBS, or maybe you also tried using PBS or adding some proteins into your electrolyte? Or can you maybe comment a bit on this selection, and if you have experience with other media?
Yes. We selected this because it is a simple representation of an electrolyte solution. I think potassium chloride is very commonly used, also in electrochemistry. And by choosing this particular one instead of more bio-related, bio-specific ones, like having proteins inside, I believe there are commercial solvents where they can simulate the synovial fluid. So that's the intercavity fluid between the knee joint. But I wanted to deconvolute these biological effects because in the next phase of my project, I'm actually going to try and use electric potential to control the friction of these hydrogels. And I want to target soft robotics applications. Mm-hmm. So that is why I have not moved into other solvents that are closer to the biospace, but this is a very good suggestion. And I believe given the targeted topic or application that I want to target, I might investigate the other solvents that you have suggested. So thank you.
Thank you.
Okay. Yeah, I think we have also reached the end of our time. Let's thank our speakers one more time. Thank you all for the great, very interesting presentations. Also the very nice mix of topics which actually do fit together somehow. And with that, we would suggest that we take a short coffee or do something else break of 5 minutes, and then we reconvene at 1600 Central European time for our last speaker